love her. I'm so tired. I didn't get back to Raleigh till like 1:04.
Oh, yeah.
I think I was scared I was going to drive all the way home. Washington. The exact opposite. They were probably like they were four,
But at least the highest.
Did you watch the game? Or?
Yeah, I was over at the
It's probably a good thing I wasn't there.
Dude, that's Spencer and Parker were having a great time.
It automatically just.
They didn't let down the third quarter. Really? Yeah. I think they sort of checked out. And then Evan stayed. Not have it. Other than that, it was like a Super Bowl style stuff. Super interesting.
Yeah, that's what a couple like went through. I don't really care about football. Like, I watch football. And they're like, well, just as a game, it was pretty boring. Yeah. Like, if you're not invested in betting on the Chiefs or the Chiefs fan, it's just like,
Yeah.
It's been really fun.
I was joking.
You got your dad, bro. It was not good. I don't know what Mahomes was on yesterday.
Or the whole line. I think it was the O line more than anything.
That's right. I was like thinking, like, did something happen behind the scenes to where they just all started playing the same like this? I swear to God, they'd be just bad, bro.
Yeah, you can wait.
6-20 was crazy.
Yeah.
If you want to.
No, they got 6 sacks. They didn't blitz. They're going to do that.
Yeah, I don't ask. We're gonna come back.
I was going to claim that you part of that true.
Yeah, Chiefs, like, we lost one time and then they came back. I'm like, probably the same thing.
You could do that.
And that's fine. But yeah, I just stopped watching the game. I was like, I'm done with this shit. I started watching the game.
That's pretty understandable. Pretty fair. I've been
Stop watching like
Okay,
that.
well,
That's
that's-
gonna break it.
I've been saying I feel bad because I was born in
I thought it was a whole game because of like, you know, what happened last time. I don't know, like,
I had so many. I don't want to make fun of them. We had fun last night, that's for sure. Oh, the Squid Game. Oh, that's what it was? I don't know, maybe. All right.
Yeah, that's what I heard. I usually watch the Super Bowl, so I didn't really have anything. I think one other one that I watched.
Kendrick was fine. It seems like they gave him way too much pleasure. Way bigger stage and all other stuff.
They gave him $4,000.
I make chocolate covered strawberry.
I didn't know they had season where.
But you.
All right, let's start. So I see that most of us actually submitted their homework. I still have very few people who did not make a submission, but the homework was due by 1 p.m. Okay. I took a fast look over the homework and I see, actually, I'm impressed that the majority of the people are solving maybe 9 out of 10 of the questions, and they have very good mathematical skills, computational skills, organization. So this was really good to see, and I hope to see an equivalent performance in the midterm. Okay. Let me check the last submission. Okay, we still have maybe 4 late assignments. 4 people, I mean, did not submit yet. I was locking the submission at 1 p.m., but after receiving a few requests, I extended that for a couple of days, but late penalty will incur. So I encourage everyone to try to submit on time this time, because I think given like 10 days for solving the assignment, and that should be more than enough for such a homework. I plan to submit or upload on Canvas homework 2 very soon. I'm just waiting probably this week to see how much we'll be able to cover out of this chapter. I'm quite confident that we'll be able to cover all of it by the midterm. I just want to have some extra time for you so that you don't have the homework submission on the same day of the midterm. I'm trying to make sure that you'll be able to submit your homework and go over it before the midterm. Maybe the last lecture before the midterm will be a problem-solving session. So I would ask you, which questions did you really struggle in both homeworks, and we can go over them on the lecture before the exam. This is my plan. I did not receive any critical comments about the homework. I see that everyone was doing very well. The grader should start today with his work, and we'll be uploading the solution very soon. Actually, it's ready with me to upload. I was willing to upload it today, but because of those 4 late submissions, I thought of giving them some more time. So today we'll extend our work. Who can remind us what we were doing last time? So we moved through the ideal transformers. We went to the practical representation of transformers, adding all the different components and trying to figure out how to get all those values in the shunt branches and even the serial branches. And we figured out that the only way to do it is to do couple tests, the open circuit test and the short circuit test. By applying those tests, we'll be able to get certain readings. From those readings, we can make our calculations to determine the missing values. So I think we're done with this section. We just had a few more things that we did not go through. Basically, there are 4 processes that do not get represented on those equivalent circuits. They are the saturation, inrush current, nonsinusoidal exciting current, and the surge phenomena. Because for those things, there's no physical representation for them. It depends on the characteristic of the magnetic material itself. So if you go to your presentation, which I've uploaded on Canvas a while ago, you could see some description about each phenomena. So basically, saturation, who has any idea about that? Why there's a saturation problem in the transformer? I think I've talked about that before. Why there's a risk of saturation in a transformer? Is it a linear or non-linear device, by the way? Let's agree on something first. Non-linear. Okay. Why? We've seen that through the equations and from some curves. I can show you something here. Getting back to the characteristics of the transformer, we said that we apply certain current or voltage on the primary winding, and then certain currents start to circulate in that winding. And then consequently, a magnetic field or flux will start to be generated in the magnetic material or in the magnet itself. But if you see how that flux B changes with the intensity, we'll see there's nonlinear relationship from the curves. I think I've talked about the hysteresis phenomena, where, in simple words, charging the transformer will not follow the same way of its discharging. That's why you see solid lines and dotted lines, which means if I applied certain potential on that transformer, whenever it gets away from there, it does not follow the same path. That's why you see two sets of lines on this curve. The other good observation is that we could see that after reaching maybe 10 amperes turn per meter of that intensity, we're getting a little bit flat, around 1.6 Webers per meter squared, which means that your magnet reached its full or almost full capability of generating flux. So there's no point in extending your intensity into 170 or so, because you'll be around still 1.6, okay? So I think here, based on this curve, reaching 10 is enough, okay? If I'd like to energize the transformer. After than that, there's no need for all that extension, because that would require a lot of intensity, while effectively we are getting almost the same flux. It's not worth it. Okay. The second issue is the inrush current. So basically, when first the transformer gets energized, it's not a linear circuit. Okay. So it will experience a very high starting current circulating in the magnet itself or in the equipment. And that value could be times the rated value. It could be, let's say, 5,000, 6,000 in comparison with 1,000, or I'm just here using some units. So it could be 5, 6 times the rated values. So from the transformer side, that raises actually a lot of tension. And there are a number of protection schemes to make sure that our transformer will not get damaged at the starting. Okay? So it should have certain capability or certain strength to avoid the breakdown. So this is the issue with the inrush current. Hopefully the transformer will be able to get energized, and then we'll reach certain stable operation after a few cycles. But this is something to consider. Usually those things are typically tested at the validation level. Like when they make a transformer, they do those tests for that. They check the starting current, the exciting current, all those things to make sure they are within the limits. Other than that, they cannot sell them, actually. They don't get the approval to sell them. Non-sinusoidal exciting current. As you have seen before, that we are applying a sinusoidal regular voltage on the primary end. However, because of the nonlinear characteristic of the transformer, the generated currents will be of non-sinusoidal structure. And that could cause problems to different machinery and to different circulations of current. So this is something to consider, that exciting current, which counts like maybe 5% of the loss in the transformer, could cause problems. So our goal is to make sure that value do not exceed that limit, to make all the necessary testing, to make all the necessary tuning, to make sure that value won't exceed 5%. So who could remind us what's the exciting current? I think it's made up of coupled currents added up together. Who can remind us of that? What about having a drop quiz right now? 10 points out of 100. Well, I think this is an easy question. It should be those, yeah.
It's L1 and the ratio of.
No, it's the sum of the I core and the IM. Those two currents in the shunt branches. So let me remind you all of them. They are here. IE is divided into those two, IC plus IM, okay? We need to be aware of that point because in the exam I might ask that question. Calculate those currents, okay? So the last thing we need to know is the surge phenomena. Thunder strikes are really a big challenge for all electric equipment. And usually surges are considered very high over voltages and they can break every equipment. Even no matter how much protection schemes we employ, they are still really a great challenge. So usually testing the transformer would require tuning the parameters to make sure that the equipment could withstand a strike to a certain level, okay? So a minor strike might get grounded, might get like absorbed by the transformer material, but typically there's certain requirement to make sure that not any storm could damage our equipment, our electric equipment, because usually those devices are pretty expensive and they are really hard to fix. So once they are broken, they are not utilized anymore. I think more things are discussed later in chapter 14, but we won't be covering that chapter in this class. Okay. Now we're getting into the important things. Per unit system. I think I've made an introduction about that before. So what's the per unit system and what's its advantage? So when I talk per unit, I'm trying to normalize my whole system between 0 and 1. For the purpose of that, it could be better understanding what's going on the whole system by simple numbers. Because I said before, in some section of the system, we'll have a ratings of 700 volts. In some other place, it will be 400 volts. In some other locations, 1,200 volts. So if I told you we made a measurement and it came out to be 1,100 volts, so you won't be able to know whether this 1,100 volt is a normal operation condition or it might be an over voltage, which might mean that there's a fault going on. So if you divide this value by those three, so you get here 1,100 over 700, it will be well above 1, maybe 1.4. This one will be like 3 times. It will be like 2.9. This one will be here like 0.9, okay? It sounds here to be acceptable value, but here definitely not. Here it's definitely not a good value. Here it's still bad, but not that much, okay? So normalizing our power system through per unit system will make everything on the same scale. This is one advantage. Second advantage, we'll get rid of referring. Whenever your system is running on the per unit system, you'll not be needing to refer anymore to the primary or to the secondary side. We've discussed those in the previous lecture. Okay, so we'll get rid of that problem. Actually, having one item to refer might cause us to make a number of calculations. But if I have 100 transformers, it will be very hard to make 100 or more referring for every component. So we get that issue solved also. So here you could read more about those advantages. I just summarized them for you. So the per unit quantity is actually the division of the actual quantity by the base value of the quantity. The actual quantity is the given quantity by me. I would say we got that measurement at that place. It came out to be that much. The base value is normally selected by you, but I will usually determine that base value. So because you might choose 100 as a base value, he might choose 200, and that person might choose 500, let's say. So every one of you is correct. You are all good. But for me, it will make me like solve the question 100 times or 60 times because each one of you might take another value or different value. So the base value is some agreed value, which we would like all of us to agree that this is the use value in the whole system. No matter how many sections do we have, it's the common used base value. So typically we'll need to determine two base values, okay? One for S and one for V. If I can give you just S alone, this is not enough. You will not be able to make V and I and Z calculations. You need two of them. So here, for P, Q, and S, they'll have the same value, same base. I normally give the S base. And then you'll definitely need a base value for voltage, whether line to line or line to ground, so that you could calculate the I base for current, the Z base, the R base, the X base by simply dividing by those. And then the Y base, G base, and B base, their base value is 1 over Z base, okay? So it's important here to start correctly from this point, okay? Normally, I would say 500 is the S base value or the base value, so you'd know that thing. So here they are saying the adoption of those two rules will ensure whenever we get the S base and the V base, same values everywhere, we'll be able to transform our system into per unit. But there's something important here. The S base is common for the whole system, while V base is bisection. Okay? We'll see what that means later. Here's an example. Per unit impedance single phase transformer. We're starting with the easy thing. A single phase transformer winding is rated at 20 kVA for 180-120 volts at 60 hertz. So he gave us the S value and the voltage ratings of the transformer. The equivalent leakage impedance of the transformer referred to the 120 volt winding denoted by winding 2 is Z equivalent 2. Is that referred to the primary or to the secondary? Yeah, definitely, because it's related to Z2, so it's definitely related to the secondary. Using the transformer ratings as base values, determine the per unit leakage impedance referred to winding 2 and then referred to winding 1. Okay? We'll get the per unit, refer to winding 2 as it is, and then we'll do some calculation and make that again for winding 1. How that should be? What do you expect those values to be? If I refer both to 1 and 2, how the per unit values would be? The same or they could be different? No. There's no need for per unit system if they would be different. Our main goal is to have a normalized system. So this is the advantage of the per unit system. Either way, we'll get the same values. Okay? So he told us in the question, take the rated values as base values. So I could note down S base would be 20 and V base would be 480. Well, this is a little questionable because even 120 works. It depends on which side you are starting with in our calculation. Both work, okay? But since he gave us Z equivalent 2, it means we are more inclined at first to start our calculation from this side, okay? In some other situations, we might start using this value, okay? But anyhow, this is the set that we need. So if you are referring to the primary side, the V base will be 480. For the secondary side, the V base will be 120. And then we need to calculate the Z base. Okay? For Z base 2, which we already have, it will be V base squared over S base, and the V base 2 is 120. We divide that by 20,000, so the Z base 2 will be 0.72. And then Z equivalent to per unit, this is how you should write, will be the Z value which we are given divided by Z base 2, okay? Make sure to define this number. It's either 1 or 2 because we might have different sides. And then we'll obtain this value. So it will be the equivalent value per unit. So now we're done with the first part of the question. The second part is asking us to refer that to winding 1, not 2. So as we remember from before, to get this primary Z, we have to multiply by A. Is that right? From the previous section? No, I should multiply by A squared. Okay? Only voltages and currents have this 80 transformation ratio of A. But for Z, we have A squared. Okay? So we need to multiply by that. And how to determine this value, AT, I just divide N1 by N2, which is 480 by 120. It's 4. So I have to multiply by 4 squared. And I got Z equivalent 1. What about Z base 1? It will be V base squared, which is now 480 for the primary side, over S base. This never changed, okay, for the whole system. So the primary side, Z base, will be 11.52. And then we need to divide our Z equivalent 1, which we obtained from here, by the Z base, which is 11.51, and then we get 0.0729, which is exactly the same as the equivalent 2 that we obtained from the other calculation. Okay, you could see that they are the same. So this is important so that we know that the per unit system will help us to avoid the referring problems in the solution, so that we use the same thing for everywhere. This is considered to be a simplification, actually, of the solution. Here are some proofs that those equations will satisfy those requirements, where E1 per unit will be equal to E2 per unit, I1 per unit, and equal I2 per unit. So those are some extra proofs for what we did. Here's the representation. If we consider the first transformer to be ideal, it will be of this shape. If we are neglecting the exciting currents, we are removing the shunt branches from here. If I'd like to have the full representation, it will be like this one. So we need to know those in case we are being asked, like, draw the equivalent representation of this transformer in its complete status, let's say, or neglecting the exciting current. Okay. Now what we have done is related to the Z per unit per equipment. But sometimes you will be given not only a transformer.
Dr. Sleeman, your audio just cut.
What about now?
That's better, thank you.
Okay, great. Okay. So if we have a transformer and an inductor and a capacitor and a number of resistors and transmission lines and generators and different type of loads, each one of them will have its own per unit. But when I put them all together, I should have a base for all. So the good thing to use is this equation here. Z per unit new would be Z per unit old, which is normally given, and then you multiply that by V base old over V base new squared times S base new over S base old. This is very important. You need to memorize this equation because it will be used a lot. So let's see an example what I'm talking about. Per unit circuit, 3-zone single-phase network. Here we have a single-phase circuit, and we have two transformers here, T1 and T2, separated by a transmission line. And then we have a generator on this side and a load from this side, okay? We can see here that those transformers are given certain per unit values, but those values of the Z load and Z line, they don't have per unit. They are in ohm. So we really need to normalize everything on the circuit. Here he's saying we need to use the base values of 30 kVA and 240 volts in zone 1. This is zone 1. Zone 2, zone 3. They are divided by the transformer location. So we would have S base equal 30. I don't put the units here, but we need to know them. And V base 1 is 240. How much would be V base 2? V base 1, I said the voltage is not constant across the system. S is constant. We're done with this. What would be the V base in the second region?
Would it be 480 volts?
480? Correct. What about the third region? No. You're not you are here on zone 2. It's 480, but the transformer rating is 460, not 480. So it should be higher. V base 3 would be 480 over 460 times 115, which should be like 120 maybe. You need to check the ratings here. You were here at 480, but this transformer rating is 460. You cannot put 115 for zone 3. It will be higher because we are moving forward. Okay. I see here he got the same calculation. V base 3 is 120. Now, so we got the V base 1, V base 2, V base 3. Z base 1 is now easy. V squared over 30,000. Don't put 30, multiply by K. Z base 2, 480 by 30,000. Z base 3, 120 by 30,000. S base is the same everywhere. And we need one more thing. We need to make sure to normalize the R and X values here for the load and for the transmission line and for the voltage source. The voltage source was 220, 0. So we need to divide that by the base value of the voltage there. Okay? So it will come out to be 0.916 as it's written here. Then we need two more things. The current base, because he's asking about the current in the load. By the end of that calculation and the transformations, we need to determine the current value in per unit and in real values. So we need to know the I base 3 because the load is here. So we divide S by V, it will be 30,000 by 120. And then we need to make sure that our transformer ratings are normalized. It was given by 0.1 per unit, and that one by certain value. Here, 0.1 and 0.1. But those are the old per units of the transformers. They don't relate to the system. So you really need to apply the rule. 0.1 times V old over V new squared times S base over the S regular S value. You can find the 20,000 here on the ratings. This is the 20. The other one is 30. Okay. So you make those changings, and then we just need to do the X line per unit. The X line was 2 from the original graph. It was 2 ohm. The Z base 2 came out to be 7.68. So I need to divide 2 by 7.68. And that would give me 0.26 per unit. And finally, the load per unit is 0.9 plus 0.2J, which I was given here, divided by Z base 3, which is 0.48. So I'll get this value here. Now I have everything per unit in the whole system, everything normalized, everything was updated for the transformers because they had old per unit values. So if I want to calculate the current which is circulating in this circuit, it will be V per unit divided by the sum of all those impedances and their per unit values. So you add up this one, this one, this one, and that one. So you'll obtain the I per unit in the whole circuit. If I'd like to know the real value, which is circulating here, I have to multiply by the I base 3, which is 250. So I multiply the resulting value of the per unit by 250. It came out to be 109.9 something amperes. So this is how normally we do the things, and they really help a lot, the per unit values, and understanding the system on a unified base. Few more things here. I see that we used wherever we were given for the S base, but sometimes that we do that when you are doing single phase circuits. In 3-phase circuits, you'll have the same thing, but we need to make sure what value we are using. Either I give you the S base 3-phase or the S base by single phase. If I give you by 3-phase, you just divide the value by 3. And related to the voltage, I either give you V base line to line, which is very often. So you need to divide that by radical 3. And the rest of the calculations are the same. Okay? For Z, I, and R, X, whatever. Okay? Yeah, those are correct. Any question? Well, I see no questions. What about MSU people? Let's go for an example then. This example is making those transformations for us, but now we are dealing with the per unit for the balanced 3-phase networks. As an example 2.5, a balanced Y-connected voltage source with EAB is 480. Is that line to line or line to ground? Okay, can we use that? No? Should we divide that by something? What? What? 3? Only 3? No.
No, by root 3.
Okay, and what? What about the angle? Yeah, we need to subtract minus 30 degrees. And it's applied to a load now of delta nature. Can we use that directly, or we could make some simplification here? How I convert that? Yeah, you divide by 3, so you make the source to be of Y structure and the load to be of Y structure. That would make the calculations much easier. And then you have the Z line, which is 185 for each phase. And he gave you S base 3-phase as 10,000. I'll use thousands from now on. And V line, V base line to line. to be 480. I could divide this by 3 to get the S base per phase. And I can divide this by radical 3 to get it also line to ground value. It will be V base, V equal 480, I think 277. So it's either way, but don't get lost. Both things, you need to make both transformations or either stay on the old three phase, okay? So here, to calculate Z base, he divided the V squared line to line over S3 base. If you don't do that, you divide this value by 3, and you divide this by radical 3. Radical 3 squared is also 3, so you'll get away by 3 by 3. You'll still have the same value, either line to line or line to phase. So eventually, this is as base here. The per unit and line impedances could be easily calculated now by dividing by this value to get the per unit. To get those, let me see. Yeah, we have a source, we have a load, and we have the line. So we need to divide the impedances, those two, by the base value of impedance. This is for the Y load. We divided this by 3, so it's now 1040. And then we need to normalize that by dividing by 23.404 to get the normalized value or the per unit value. Okay? And then he wants the V base line to ground. We just divide 480 by radical 3. This is what I got here, 277. So, and he's normalizing the voltage. We were given with this value, 480 and angle 0. So he divided by radical 3 and subtracted 30 degrees from the angle and divided the V base line to ground. He divided by this value, which is the base for the single line to ground. So it came out to be 1 per unit. Eventually, if I want the current which is circulating here, I'll divide this voltage by the sum of those impedances, and that's what he did here. But I'm asking about the real value of the current, so you need to get the base value of the current. So either you get S base 3 phase over radical 3 V line to line, or the another equivalent form for I base is to use S base single phase over V base line to ground. So you would divide here by 10,000 over 3, and down there you would divide by line 277. I think those should give the same value. Okay? So you get 12.3. If I ask for the real actual value of the current, you need to multiply this value by 2.147 to get this value here. It will be 25.8 amperes with this angle. So this is typically how we do the per unit system. Okay? Questions? Any question about the per unit system? This is very important, by the way. Probably it's one of the most important in this course, because you'll use that later if you take more power courses, mainly in faults calculations and stuff like that. Well, if there's no questions, I think we still have some good time now. Let me start with the next topic, which is, we will make some short introduction for that. We have been talking about the three-phase transformers shortly before, and we said that they are just adding 3 single-phase transformers to each other and making some connections between them so that they operate in a single unit. There are a number of advantages of having the 3-phase transformers. At first, they can deal with the 3-phase power transmission, which is very common. The second good thing, their capability is much higher and their ratings are well higher than the single phase equipment. But their issue is that they get really harder to calculate and to work on because of this phase shifting. Normally, if they are star to star connection or Y to Y, they're like that from both sides, they could be easy to solve, or delta to delta. The main issue happens whenever they are of this format, because we have that 30-degree phase shift in each transformer, so it makes it harder for us to predict the outputs of that transformer. So we'll get to know how do those things work out. So let me try to draw this thing now and to see how to make those connections. So we see here that we have 3 transformer units. The primary side, they use in the book the notation H, and the secondary side, they are using X, okay? So I'll have 3 windings from here. And 3 equivalent windings from the other side. So I'll have here H1, H2, H3, and here I have X1, X2, X3. So on the high level of the transformer, we have capital letters A, B, C, and here we have A, B, C. So now we'll be applying certain voltages, VAN, VBN, VCN on all the primary sides. And we will get, after some time, VAN small. Here we have VAN, and here we have VAN on every side of the secondary section, okay? And we also apply like IB from here. We get from here IB small, and from here IC small. Here IA small, okay? So this is an easy structure here. It looks to be star to star, and we have a grounding connection. So here I just have 3 single-phase transformers, ungrounded, and I don't see right now if they are star or delta connection. This is my next step. So to make a ground connection, I need to make sure that they are all connected. This means that there's no connection here. They are commonly connected to a ground. Here's the neutral. And I think I'm done now. This is how the Y connection is. And you could repeat the same thing from the other side. I think this is an easy representation because we don't see here a phase shift. If you see the circuits, you typically have phase A, phase B, phase C. They are all balanced, and those are the output sides, A, B, C also. The issue happens later with the naming and how to predict the outputs. So on this side of the circuit, because they are both balanced and they are both of the star connection, the shifts are in phase. Actually, they are preserved. There's no angle difference between both sides. You see here, schematic representation showing the phasor relationship for positive sequence for both circuits, for this side and the other side. Here they are explaining the things that I was talking about. Here's the issue which start to show up. We have the same connection on the primary side like this one, the star, but here now we have a delta. And on purpose, I did not draw the second side because I want to draw it here for the delta. For the star, it will be from the other side the same. But for the delta, it's different. Because here, in order to make a delta, we need to have a connection between this one and this one. Okay? And then it goes to here and then goes out into this transformer. So you could see the connections between the transformers. And then I need to clear those to make it nicer. Anyhow, you have the nice figure here. I'm just trying to emulate the things. So effectively, this is the main difference between the star and delta connection. In delta, by the way, I may not name them in the exam or in the homework. You just need to see the figure and figure out whether it's a phase or delta connection. So I think I need some time for this determination of the input and the output angles, but I just need to take a look at the attendance. By the way, today or tomorrow is the due date for the student enrollment evaluation, where I'm required to submit the names of the people who stopped attending or not attending the class. And they have 2 days to figure out what to do, or they will be dropped from the course. I see very few people of you are not really attending. In normal cases, if a student has something urgent, I would waive his attendance, like here. This blue color means waived attendance, but the pink one is a dangerous one because you missed a class. So primarily, they are requiring you to be in the class. So I remind everyone who signed up for the class in person have to attend here in person to take the attendance credit. But I don't think anyone will be reported for that survey. I need to check a few names here later today. Other than that, do you have any questions for me? No questions? Okay, see you on Wednesday.
Few minutes late. Can I sign this real quick?
Okay.
Oh, yeah. Actually. Are we actually joining?
So, I wanted to let you know that Friday I have an appointment. Would it be okay if I was excused for
What's your name?
James Menegoni?
This one?
Yes.
Okay, I'll waive that attendance for you.
Thank you. No, but Friday.
Yeah, I know.
I have the slip that you asked for a while back.
Mhm.
All those dates are Fridays that I could be gone.
What about the midterm?
Okay, yeah, that I will be gone for conference.
Well, you have to make the exam. You need to confirm that by email to me. And the only time to take the exam is 1 day before that.
Okay, I think I can do that.
It's either Thursday or Friday. No exams after Friday.
Right, yeah, definitely not after. I understand that.
Okay, but you need to let me know ahead.
Yeah, for sure. That's
Right,
2 weeks
right.
from now, right?
Yeah. I think,
that's when
yeah,
the meet
it's
will
like 18 days from now.
Yeah.
But at
Yeah,
most in a
oh.
few days, I need to receive a confirmation of that.
Sure, yeah. I'll
Because you'll be tested in the testing center.
Okay.
I will not be available to, I don't have place for you
Mhm.
and the other people also to make another exam. So we made an arrangement. So in case anyone cannot do the exam on the date, it must be done 1 day before. But we decide on the time.
Yeah.
So they would tell me we are available at that time. So I'd say, okay, let the student do it at that time.
Okay. Sounds good.
Okay.
Thank you.
Bye.
Hey.